Hello and welcome to EE 233. I'm your instructor, Gregory Myers. In this video, we're going to take another look at pointers. This video is part of a larger series of videos falling under the pointers demo, with this video specifically focusing on two functions that allow for us to pass variables that can be edited by reference or by address. Specifically, what we want to do is, in our first example, we want to take a look at a function that accepts one variable, that contains a single value that is passed by value. In other words, a copy is made inside the function. And the second variable then is passed by reference or by memory address. And that means that that variable can be modified inside the function. This frees us up to also have a return value, for instance, that might provide exit success or exit failure. In the second example, we extend this concept a little bit further than to look at the behavior of arrays when they are passed to a function. And what we're going to discover is that arrays in C are passed by reference by default unless we specifically ask that they are not editable. In other words, that they are asked to be constant. Likewise, in the second example, we are also using an int return value to be able to return back to the calling function an exit success or exit failure. In this particular video and in future videos, I'm going to be very careful to use the word return to indicate the value that is returned by the function. In other words, the value or the data type to the left of the name of the function. We will not refer to values that are updated when the variable is passed by reference as being returned. That's a critical difference because in both of these examples, we are giving the function direct access to a location in memory that it can edit. So without further ado, let's go ahead and grab a copy of our pointers 03.c. We'll go ahead and move our function signatures or copy our function signatures over to our list of function signatures in our pointer driver, and then go ahead and add the code that I'm providing for you to the bottom of your function, or excuse me, your pointers driver .c. Now, as in earlier examples in this series, I've already given you the code, so the only thing that we need to do is to essentially wire it up in our main. In other words, to be able to handle the switches associated with the functions that we wish to call. So at this point, then what we can do is we can just borrow a couple of our earlier examples here. And in this case, what we'll do is we'll simply handle the version 5 and the version 6. And once again, I would encourage you to spend a little bit more time on your documentation for this so that later on, when you come back to these examples, they will mean something to you. In addition, we can also update the version of our if-else-if that will allow for you to call all of our pointer examples. And once again, this is completely optional, but at the very least, you probably ought to take just a second to update your help. Once again, as we get further into this series, we'll stop spending as much time with this, but I'd like for you to get into a habit of doing this just simply because it helps later on. At this point, we should have functioning C code, so it's probably worth going ahead and building it. And at this point, we can then test from our command line whether or not our application works. And so we'll start off by simply passing the name of the exe, and you'll see that we are getting our ever-increasing list of help switches. And at this point, then what we'd like to do is we'd like to take a look at our example _add_1 version 5. Now, I'm going to go ahead and run this, and I'm going to go ahead and attempt to split the screen here between my console and the code associated with it. I'm very careful here to see if we can't utilize the screen here. All right, good. And what I want to do is I want to go ahead and jump to my add one version 5. Now, just like the earlier videos in this series, it's comprised of 2 parts. The example, which essentially is a driver function, doesn't accept any inputs or return any values. Instead, it just sets us up then to call our little helper function. And our helper function, we'll take a quick look at, accepts a integer a by value. In other words, you essentially get a copy of that value. You have a local memory storage for that value. And inside this function, it is known as int underscore a. Additionally, you get a memory address or a pointer to an integer. And we'll know that, notice that is int b, int underscore b. And what we do in this example is we simply add 1 to whatever value is passed to A, and we store it at the location of B. In other words, we're updating the value at B. Remember that we are being passed an address, so we have to use the asterisk in front of the int B to specify that we wish to add 1 to the value stored at that location. Now, additionally, inside this little helper function, we are printing out not only the value at A, but also the address of int A. But notice this is a little bit different here. I'm actually specifying the asterisk once again in front of int B for printing out the value of int B. In other words, I'm saying I want the value at int B. And then notice that when I ask for the address of int B, I don't have to use the ampersand. This is once again hopefully emphasizing the difference between passing a variable by value versus passing it by reference. Now, going back to the main function, this essentially just sets up what we're trying to do. We create the 2 temporary variables, in this case are A5 and B5. We initialize them to 0. And I'm once again simply showing you the values and the addresses of both. And in both cases, you'll notice that I'm using the ampersand in front of the int underscore A5 and int underscore B5 to emphasize that I want the address. And that's what you see over here in the console, the values and the memory locations associated with those variables. We then make a quick call to our helper function, which you'll notice here that since int A is passed by val, outside of the function, the value is stored at FECC, but since we have a copy of our int A inside the function, it has a different local memory address. In other words, this address right here is allocated inside the function. However, if you look at B5, particularly the address of B5, which is FEC8, since we are passing the address to the function, inside the function, int B is also known by its address of FEC8. So essentially, it points to the same location in memory, which allows for us to then update by adding 1 to 0 to get 1. It allows for us to update the value at FEC8. Now notice when we return back out of the function that I am using the return exit success. Now, we didn't have any logic in here, so we really didn't have a way of failing on this particular one. But the idea here is that this is sort of a separate communication channel back to the calling function. So we can get more sophisticated with our error messages by returning the results of our function, but updating the by reference variables. So note the distinction here. We are returning an integer, however, we are updating our int underscore b, or specifically, we're updating the value at the address associated with that variable. Now, if you take a look outside of our function, in other words, when we go back to our calling function, you'll see that nothing has changed about our A5 variable. Its value is still 0, its address is still FECC, but our B5, the value is now 1, but the memory location is still FEC8. So essentially what has happened here is that our little helper function has the ability to update the value at the address corresponding to the int underscore B5 variable. Now, I would encourage you to pause the video at this point and make sure that you are completely comfortable with this concept, because in the next example, we're going to take this a step further and we're going to look at arrays. In other words, variables that hold multiple values of the same data type. Now, looking at our example add1 version 6, you'll see that it too has a little helper function, and its helper function is a little more complicated than the previous one. Specifically, in addition to an array, we also have a constant array. And so the first input argument is a constant array of integers, which means that it cannot be modified. The second input argument is an array of integers. And what we're going to discover is that if you do not specify the constant in front of the array, that it can in fact be modified. Well, why can it be modified? Well, that is because arrays are passed by reference. In other words, you pass an array of values by simply specifying the address of the first value, which brings us to the third input argument, which is our n. Our n simply controls or tells the function how many integers, in this example, how many integers are in our int a and int b. Now, note here that I'm using what concept was referred to as parallel arrays, meaning I'm making the assumption that our int a and int b are in fact the same size. They don't have to be the same size as long as the n reflects the array with the smaller or lesser number of values. Okay, so as long as n is the count for the smaller array, you won't have any problems. But typically when you pass a single n like this, you're assuming then that these parallel arrays have the same number of elements. Now, what are we doing inside of this function? We simply are printing out the value at the 0th location. We are also printing out the address of the beginning of the array. Likewise, we do the same thing with B and the address of B. And you'll note, once again, the only difference between A and B is that A is constant, where B can, in fact, be updated. Now, what I'm doing inside of this for loop is I'm using my temporary index variable to simply loop through all of the elements in the array, and I'm taking all of the elements in my int A array, and I'm simply adding 1 to it, and then assigning that value to the corresponding location in the int B array. Now, you'll note I've left a little comment down here, something that just for you to try. If you were to uncomment this, you'll actually get an error on compile. Effectively, what I'm doing here is I'm attempting to set the value in my int A array. But remember that my int A array is supposed to be a constant, so therefore I cannot make any changes to it. And sure enough, you're going to get an error when you try to do this, because int a is specified as being constant. The last step here is I'm simply proving to myself that I've managed to update at least one of the values in my B array. In this case, I'm just spot checking, if you would, the 0th element to see if, in fact, I've made any changes. Now, before we go any further and we take a look at our example, what I'd like to do is to go ahead and run our version 6. And you'll see that we get a much longer table. And the reason for that being is that I want to show not only the value at a specific location in memory, but I actually want to see the address of that location. So what we'll do is we'll start off with 2 separate arrays, both of which are going to be hard-coded to 10 elements. This, of course, can be turned into a variable later on if you wish to play around with it. But in this case, what I'm doing is I'm doing a one-step declaration and initialization in which I am initializing my A6 to the values of 1 through 10, such that the 0th element is 1, the first element is 2, so on until the 9th element, which would be 10. The second array, I'm initializing all of the values to 0. Once again, I'm showing you this shorthand notation just so that you're aware of it, although very often you will discover that its shortcomings mean that you're going to want to use something like a for loop to initialize your arrays. And in this case, what I'm doing here inside of this for loop is exactly the same thing as I did above. I'm simply assigning the value of the index to the location associated with that index. And actually, specifically, if I want to maintain the relationship between the index and the value, what I would want to do is I would want to specify index plus 1. So note here that my value is equal to index plus 1. It doesn't matter if you change this or leave it alone. Just make sure that whatever you do matches what we're about to see in the command line. So I'm going to go ahead and build it once more. Clear my screen, and we're going to focus just on our version 6. And you'll see here that in my table, I start by printing out the value of the 0th element in my A6 array. And I follow that up with the address of the int A6 array. And you'll notice here that I can do that one of 2 ways. I can either specify it without the ampersand or with the ampersand. And that is because arrays are handled or accessed by address. In other words, the first element of the array, or the address of the first element of the array, represents the address of the entire array. Put another way, the address of the entire array is simply the address of the first element. Which brings us to the next concept we want to look at, and that is the idea of size of an element. And in this case, what I'm doing is I'm leveraging the size of function to get the size of the entire A6 array. And in this case, there are 10 integers, and if you recall, an integer is 4 bytes, so we would assume that the entire array is 40 bytes. You can also go ahead and run the size of function against a specific element in an array, and in this case, what we're getting is the 4 bytes associated with an integer. Now, in this for loop, all I'm doing is I'm leveraging my index variable again to simply loop through all of the elements in our array. And I'm simply printing out in this first line the value associated at a particular index. In other words, in this case, I'm going to see that my value at A6 square bracket 0 is 1, which we already knew from earlier. But also note here that I'm specifying the address of my A6 square brackets index. In other words, I want to know what the address of that first element in the array, or the 0th index element in the array. Well, as I mentioned earlier, the address of the 0th element in an array is the address of the array itself. Now, if we continue through this for loop, you'll see that I am simply incrementing the value by 1, which is what we set up inside of our for loop. But notice also that the addresses themselves are incrementing. And to understand a little bit more about what's going on, let's take a look at how do we store an array of 10 integers. Well, if you think of an array as simply smaller boxes, each containing an individual value, then it starts to make a little more sense. I have not included the full hexadecimal value, but rather only the last 2 hexadecimal values. In this case, the last 2 of values in my address are A4. And if you'll note here, if I come back over to my console, you'll see there is the full memory address for my array. Now, to keep it simple, I'm just going to focus on the last 2 values. Now, if you recall, for what we just saw, an integer can be stored in 4 bytes. And you'll now see that the difference between the neighboring addresses, so in other words, the address of this first box is A4, and the value or the address of the second box is A8, which corresponds to 4 bytes. Likewise, if you continue on here, you'll see that each one of these increment by 4. So in this case, what we've got here is our sequence of boxes or sequence of memory locations associated with the storage of integers in an array. And just a little bit of a side note here, remember that with hexadecimal, which is base 16, it's going to be, in addition to values 0 through 9, you're going to have A, B, C, D, E, and F. And as a quick reminder, A4 plus 4 is A8, A8 plus 4 is AC. Why is that the case? Well, because 8 plus 1 is 9, 8 plus 2 is 10, which would effectively be A plus 3 is B, and 8 plus 3 is B, and then lastly, 8 plus 4 is C. And I just saw we have a little bit of a typo here. Do want to take just a second to correct this. No, it is actually correct here. I'm sorry. I was jumping ahead to our next example. So I was jumping ahead to our next example here. So our A8 plus 4 is AC. And then when we add 4 to our AC, we're going to get B0 because C plus 4 is going to be 0. Okay, so continuing on, we do the same thing now with our B array. We'll start off with the value associated with the 0th index, which you'll see here is 0 because we set the entire array equal to 0, so no surprises there. Likewise, we will get the address of the int B6, which you'll note here is our FE7C, which corresponds to the address of the entire array. You'll note here that there's the size of B6 and the size of an individual element in B6. Essentially, since it's an array of integers, just like the earlier examples, there should not be any differences there. But then notice here, once we get into calling our function, it accepts two arrays, and then we've hard-coded the value of 10. Now, this hard coding here is completely optional. You could use a variable and ultimately have a variable size for our arrays as well as for that third parameter. But you'll notice now inside of the function, all I'm doing is simply adding 1 to each one of the elements inside, or excuse me, to each one of the elements in our int underscore a array. So where the 0th element of our int underscore a was 1, then we would expect the value of 2. So 1 plus 1 is 2. Continuing all the way through until the 10th element of our int underscore a, which was 10, which would mean that we would be adding 1 to 10 to get 11. So the value stored in our int b would be 11. Notice, as I said before, we are utilizing the return value simply for exit success and exit failure. We are making no updates to our int a array, but instead what we're doing is we're making updates to our int b array. And as I mentioned before, we are treating these as parallel arrays. Returning back to our calling function, we do the same thing that we did before, although it's slightly abbreviated in that we are only interested in seeing the changes in our arrays. You'll note here that I'm printing out all of the values in our int A6, starting with 1, going through 10, and then likewise all of the values in our B6, which will be 2 through 11. So in other words, our B6 was in fact successfully updated. Now, the last thing that we want to note in this particular example is that we did not specify by address. In other words, we didn't use an ampersand when we passed our int underscore A6, nor do we use an ampersand when we specified our int B6. So what I want to do for just a second is I want to focus in on this part of our table. And I also want us to make a quick note of what the original addresses were for our A6 and for our B6. You'll note that our A6 was A4, FEA4, and our B6 was FE76. Inside the function, you'll notice that the address of int underscore a is still FEA4. And the address of our int underscore b is still FE7C. However, even though both of these arrays were passed by address, we cannot modify this one because we specified it as being constant. However, we can make all of the modifications we want to B because we know, number one, the address of the first element in that array, and we also happen to know the number of elements in the array. So hopefully you have found this video useful. As always, if you have any questions or comments, don't hesitate to email me, and thank you for watching.